Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to the continuation of the previous lecture on the magnetic materials. Towards the end of the previous class, we were looking at the magnetic moments, because the chi, which is magnetic susceptibility, is difficult to handle in terms of comparing, explaining, etc. So, I have explained the two types of components. Whatever you measure is the total magnetic moment that you will measure, magnetization you will measure. There is magnetic susceptibility, and from the magnetic susceptibility you will calculate the magnetic moment, and that is a total one. And the components what contribute to the magnetic susceptibility is, one is the spin as a maximum and other is orbital to some extent. In transition metal, I also told you this magnetic component coming from the angular momentum is somewhat minimal, or sometimes 0, most often 0 and sometimes minimal, but whereas the same thing in case of a lanthanide, it is a very important value, very considerable value. So, therefore, we have materials with the both the spin and angular momentum together. There are materials which is mostly of the spin. Therefore, I told you in the previous class that we can make a combination of the lanthanide with some lanthanides, lanthanide with transition metals, transition metal with other transition metals, and variety of these kind of things can be made to make the magnetic materials. Okay, all this obviously depend on the number of unpaired electrons, the spin value, and the position of the electrons in the D system or in the F system. So, both of these are absolutely important. For example, if you look at the simple coordination chemistry aspects of it, and you can see the spins are important to calculate your mu. Unpaired spins is very important. That is dependent upon to what level is the crystal field is splitting. So, please look at the slide, and so if you have a weak field, then you will have the from ground to excited state difference, which is the crystal field splitting is smaller. If you have a strong field, the crystal field splitting is larger. So, larger means that that you have a much higher, greater energy to go into the excited kind of a state. So, the weak field, the higher one can be easily filled, and in the strong field the higher is not so easily filled with the electrons. So, therefore, you get the spin arrangement. This is for these are two situations for the same ion. This ion is a D4 ion, that means 4 unpaired electrons in this. In one situation, let us assume the metal ion is in the field of the ligands. The field means field of the ligands. Each ligand is electric charge. So, therefore, in the electric field of the ligands. So, this will where you have 3 orbitals with 3 electrons and 1 more. The fourth could either the pair or go to higher, since the energy difference is smaller. Therefore, it would prefer to go there, because when you try to pair, there is also a repulsion. This repulsion energy versus the gap, that is what decides whether it will pair or whether it will go. That is all. So, that is where. So, if this value is small enough, then this need not pair, it will go. So, that means you have 4 electrons, 4 unpaired. So, your N becomes here in this case in the D4. So, if you have a weak field, so what we will have? So, the N is equal to 4. And on the other hand, if you look at the other side, please look at the slide. I am looking at showing this. So, the 4 electrons are in the same here. So, 1 pair and 2 unpaired. So, that becomes in the strong field the same D4. The D4 is not changing. So, in the strong field, so this becomes the N becomes 2. So, you know that this is N into N plus 2 Bohr magneton. So, this will become 4 into 4 plus 2, 6, 6 into 4, 24, square root of 24, 4.9 or something. Here is a 2 into 4, 8, So that will be 2.85 or something like that. See how much difference. So your magnetization, magnetic moments, your magnetic susceptibility also vary accordingly, and your magnetic moment changes. So therefore field strength is also another parameter now you are looking at. Earlier we have seen temperature, now you can see the field. So another example is shown here on the slide for a D6 thing. So D6, so 1, 2, 3, if it is small, weak, so you can put only 2 here, then the next one will come here, not here, not here. So you know very well. So therefore this will become 4 unpaired electrons. So that will be equal to 4 unpaired electrons. On the other hand, if you have a strong field, you have a huge gap is there, therefore it pairs, because the repulsion will be weaker as compared to what you have the field splitting, all 6. So what is the net N? 0. So this becomes a diamagnetic for a D6, this will become a highly paramagnetic. This has got N is equal to 4, and this is a thing. So in case of D6, so weak field N is equal to 4, and strong field N is equal to 0, no unpaired electron at all. Okay, N is not total number of electrons, N is unpaired electrons. Okay, so you can see. So when you have some little time, you sit and look into all these, the crystal field, low spin, high spin, etc., all of these. Not so much important for this particular course, but this is with respect to the thing. But those who are interested can go through all this, different configurations in the weak field for the same in the strong field. So D4, and then D5, and then D6, and then D7. You can see that already shown on the board, both the D4 and D6. So you can sit and work out all other as well. What I mentioned to you, number 1, when you put a compound in a magnetic field, you are putting the total, you are not putting only electrons or the orbital, you are putting the total. So you get what you measure is the total magnetic component. But this total component comes from, one is major component comes from the spin, some minor component will come from the orbital, or almost 0 sometimes for the transition metals, and for the lanthanides it will be quite considerable. That is what we said. Now you can just look at what kind of electronic configurations are suitable for giving this kind of the orbital contribution. So if you look at the transition metals with the octahedral T2G and EG, or tetrahedral, T and E. So in these cases, if you have a partially half filled or partially fully filled, so in this kind of thing, like that means 1 electron here, that will be, that can move here, then can move here, etc. So therefore it can have a orbital momentum. If you have 2 electrons, so also it can move here, this can move here, and if you have 3 electrons, no. Then if you have 4 electrons, then if you are here, but no, but if it is one of them is paired, then yes, you can have. So unsymmetrically filled T2G or T2 in case of tetrahedral can give rise to this orbital contribution. Of course, spin is always when it is free, when it is not paired, it will always show. So which of the things will show? T2G1, yes, that will be whether in the octahedral case, not in the tetrahedral case. Tetrahedral case, this is in E, and T2G2. So these green ones are in the octahedral field, the red ones, the green ones will show the orbital contribution, the red ones will not show the orbital contribution. So you can see these two shows the orbital contribution, this will not show, these two will show, this will not show, this will not show, this will not show, this will not show. That means all the EG configurations will not show. Okay. So for this, for low spin, for the high spin, D1, D2, D3 do not make any difference, only D4 onwards it will make a difference for high spin. So the D4, D5 low spin have a orbital angular momentum, and these do not have. You do not need a mug, you just need to simply put the electron and see whether it is in an unsymmetrically filled T2G or is it in the EG. That is all you need to know. So you do not need to remember mug, please do not do that, and D6 and then D7. So similarly here. So you can see all of them, but this is what one expects that not happening in those cases. For example, here the D8 octahedral, So, all these they do not show any orbital contribution. Now, suppose you look at the nickel compounds D8 and the copper 2 compounds D9. So, as per this they are not supposed to show any orbital contribution to the magnetic moment. OCMM is orbital contribution to the magnetic moment. Okay, but several compounds, not all compounds, several of the compounds of nickel 2 as well as copper 2 shows the total measured magnetic moment, which is called the mu observed, is also known as same as mu measured, is same as mu S plus L. So, that is total magnetic moment, which is a measured one, the experimental one, whatever you call observed. Some people write as mu experimental. Okay, all of these. So, these values, okay, are greater in many cases. That is not possible because of the configuration that we have seen, but it is possible if you take to one of the electron take to the higher energy level. That is what is called excited state. I have some example, I will show you that. So, when it goes to the excited state, in case of this, what will happen? You have originally in the D8, originally you have T2G6 Eg2. Now, what I am saying, you take one of the electron and put it here. So, that is the excited state, this is ground state. Now, D8 in the excited state. So, in the excited state, I will put T2G5 and I will add one here Eg3. Number of electrons are same 8, 8. So, D8. So, now here you have created an asymmetry of the electron filling, therefore, you have your orbital contribution. So, if you have the orbital contribution, your total measure value can be greater than the spin only value, and that is what. So, that means this is in the ground state, it will not show, but in the excited state it will show. So, excited state can be accessed depending upon if the gap is smaller or if the temperature is higher, many things, many possibilities are there, but whatever is there, I have explained to you the concept of that. So, the excited state population is more common with the tetrahedral structure as compared to octahedral. Why? Because tetrahedral crystal field splitting is always smaller, 2/3 of what is there for the octahedrals. Okay. Also, weak field, even if it is octahedral or tetrahedral, it does not matter, weak fields, the gap is smaller. In that case also you can have excited state. Or suppose you have some ligands which brings in a lot of covalency, like iodide versus bromide, iodide versus chloride, etc. So, then also you can have, both of them are very similar in terms of the field, but their the effect on the crystal field splitting is different because of the covalency. So, all of these parameters, so all those are explained here in this particular paragraph, please go through those. So, all these are capable of making that. Some little exercise is given at free time, you can look into. So, the D4 with the high spin, low spin, D5 with the high spin, low spin, etc. With one unpaired electron, the mu effective is 1.8 to 2.5, but actually show, if it is only spin, it should show only within 1.8. Some of the compounds will show even up to 2.5, for example, some copper, other things. Okay. And with the 2 electrons, it is supposed to show 2.85. And there are a large number of compounds which show 3.2 to 3.3 or 3.4. So, all of these are coming because of the orbital contribution. That could be either directly at the ground state allowed, or some of them is the excited state allowed. So, whatever I explained to you just a while ago on the board is shown over here. The nickel octahedral D8 T2G6 Eg2, no contribution from the orbital, and the excited state T2G5 Eg3, it can contribute. Similarly, you take cobalt 2 plus tetrahedral D7 ground state E4 T23. T23 will not show. But then you take one electron from this E to put into the E3 T24, that will show. So, now you understand, you have examples of all this. So, octahedral, experimental octahedral nickel 2 always be less than the tetrahedral. Reason is tetrahedral, the gap is smaller, so you can have more and more the excited state filling, all those kinds of things. So, the ligands, sometimes even the ligand environment can influence your magnetic moment depending upon their distortions and other things. So, when you distort, what will happen? your d orbital splitting will change. So therefore your distance between the d orbital things, everything will change. So therefore you will have. Okay, now we have seen the low spin, we have seen the high spin, we have seen the spin contribution, we have seen the orbital contribution. Now can we go from one spin to the other in the same compound? Yes, it is possible. So if the energy difference between the one spin state and the other spin state, what is one spin state? Let us say high spin. What is the other spin state? Low spin, or the vice versa, low spin high spin or high spin low spin. If this difference in their energy is smaller as compared to the kT, K is Boltzmann, T is temperature, then you can have population for both. So that is what. So these are nothing but isomers, but what kind of isomers? Electronic isomers. So please look at this. So example is shown here on this slide. The low spin, this is shown for a D6 thing. The low spin for an octahedral D6 we have already seen 2-3 times in this particular class already. All the 6 electrons are paired into 3 pairs, and then for a high spin, then you have 3, then you have 2, then remaining 1 will be pairing here. So that is what you have. So you have 4 electrons high spin. If you look at the low spin, it's very highly colored. If you look at the high spin, almost colorless kind of thing for the same compound under different temperatures. This is by different temperatures. Now if you plot that chi, I have shown you in the previous class, the chi is the representative, chi is the measurement, mu is not measurement. So mu is only a calculated value, you convert and use it. So now if you go from this low temperature and then start growing this, so almost no change in the chi, but sudden good change in this, and then saturation. But when you are reversing the temperature from the higher side, then you are not going back in the same. So you can see that it is going back. So this is what is referred as a hysteresis, is a magnetic hysteresis. That means magnetic force is being stored in that particular compound as a result of going one cycle of increasing temperature and another cycle of decreasing temperature. So this is by doing. So that importance we will see in a while later on. Now you can see if there are 2 magnetic centers, this one paramagnetic, another paramagnetic, connected by this ligand. So let us say this is one iron center, this is another iron center, etc., no problem. And if these 2 are both in the low spin, there can be low spin, high spin, both can be high spin, high spin. There are 3 combinations are possible if there are 2. So therefore your coupling will depend upon how these are connected with that. So your net value of the magnetic moment or magnetic susceptibilities will vary depending upon this. This coupling we will study in a later slides, how is their coupling values. Just take simple case of this. This is the 110 phenanthalenes. So 110 phenanthroline is the one which is a bidentate chelate with 2 nitrogens. So you can see one nitrogen, another nitrogen is a chelate, second chelate, third chelate. So all the 6 coordinations are filled on the iron center, and this is iron 2 plus. Now this shows at the room temperature 300 degree Kelvin is low temperature, room temperature. It shows a doublet in the mass buoyer, which I have not talked to you. I will be talking to you a bit much later, maybe after 15-20 classes later. I will be talking that in this particular course, but you can always look forward for that. And it gives a doublet with a very small gap. As you decrease the temperature from room temperature to 240 to 80 to 5, what is happening is not so much change is happening over the period, over a temperature range. So your magnetic material, that whatever is there at room temperature is the same even at that particular low temperature. But on the other hand, instead of 3 chelates, I make into 2 chelates. So 2 of the 110 phenanthroline, and the remaining 2 coordinates are made with the NCS ligand. So that is the NCS ligand, where iron is bonded to that. This yellow is the sulfur, this is the green is the nitrogen. So this is NCS. Now you do not have a chelate ligand, so the stabilities are obviously different. And now if you see that this particular compound at room temperature will not show the low spin, will show the high spin. See how greatly at the same temperature is not even changed. Here the material is different. This is a different compound, this is a different compound. Now as you keep reducing the temperature, going low and low, these are the greater gap between the two lines is the signature for the high spin, and you start seeing something inside which is similar to that of that. That means you started populating low spins. So you have a high spin at that temperature, you go to down to let us say 180 thing, then you have those, plus you have some small with a smaller gap, that means low spin, then you have further low spin, and you go to liquid nitrogen temperature which is 77. So that means you can change the behavior, magnetic behavior of these compounds as a function of temperature, and here also as a this is for the same compound, this whole thing is for the same compound, this whole thing is for this compound. So for this compound you are not able to change anything, for this compound you are able to change the magnetic behavior as a function of temperature. You can solvent can also change. So suppose you take this particular compound iron 2 picrate thrice, okay, and having Cl2 outside because it is a 2 plus, and there are some solvents, okay. So one this ethanol, other solvent is methanol, other is 1 water, other is 2 waters. So for all these 4 cases, these magnetic measurement vectors are drawn here. You can see for ethanol it goes this way, and if you take methanol it goes this way, and if you take water it goes this way, and for this so they have a different transition temperatures where the magnetization is going from low spin to high spin. So low spin high spin transition temperatures are dependent on even the solvent. They are not even directly bonded, but they are quite influential in these things. So you can look at the crystal structures if you want to know further, okay. So these are important things. So therefore your solvent binding at the metal center can also show a change in your magnetization behavior. In other words, low spin high spin crossover temperature. So this will cross over at this temperature. For ethanol it will be crossover temperature will be between 100 and 150, and for methanol it will be little higher than 150. For the water it will be close to 200. If it is with the 2 water molecules and the coordination sphere, it will be almost close to 300. So it's going from 100 to almost 300. So you are changing so dramatically your transition temperatures. So that means this compound, if you have, you can use at room temperature itself as a spin crossover material. So let us look at some example of application of spin crossover. So here is a spin crossover. You use obviously the cords, the magnetic cords in various contexts. You are using always that. You can see that the magnetic cords. So then you put the laser and the laser heats, and then based on that you are going to change the magnetization. You have seen earlier in the previous slide here, please look at that. So as a temperature variation on this one, you can see temperature variation on these things. So this property what you are using is low spin to high spin to low spin transition, only the property, magnetic property you are using in all these cords. More details are not required for this particular course. How it goes, when it goes from a high spin to low spin, what kind of a geometry changes that is showing, but that is also not very important for this particular course at all, but information is given, you can utilize that. So you can take the low spin, go to high spin, or you can take the high spin, you can go to the low spin by changing temperature, by changing pressure, by putting some light, by putting some magnetic field, many parameters, any different kinds of things. So whatever is, so that based on that your application will be built, easy or okay. So when you have two magnets connected together, there will be a magnetic coupling. So they can be coupling. So this is one paramagnet, this is another paramagnetic center, but these two are connected through the chemical moieties, through the coordination within the same. Then what will happen? These two vectors could, not the atoms, could vectors, the magnetization vectors could be aligned completely, could be aligned halfway, could be aligned completely opposite. So again based on within intramolecular ferromagnetic, intramolecular antiferromagnetic, intramolecular ferrimagnet, all these are possible depending upon the. So how such a orientation can make, that we will see just in this, based on this slide itself. Okay. So suppose you take the MNO MN here. So this is a, this angle is 180. If you take this angle is 180, that's very important angle is, and then these orbitals overlap in this direction. So this will induce and this. So, you see this is a up spin, this is a down spin. So, these two are antiferromagnetically coupled. Okay. So, that is. On the other hand, come here on the slide on the top, here it is a cobalt, 2 cobalt centers, but there is a little flexibility of this, and so you can see that is shown as like this flexible arm, flexible connectivity between them can make the two orient in the same direction also. So, therefore, orbitals in between are important, flexibility in between is important. So, therefore, angular orientation of the two of these depend on how it is connected. So, therefore, these two vectors are on the same direction, therefore, they become exchanged ferromagnetically, not antiferromagnetically, ferromagnetically. So, you can see the magnetic force diagram here, but it is not very important, this magnetic force diagram here. Now, look at another thing here, it is a copper one center, copper another, but there is a highly flexible kind of a thing you have here. So, therefore, this also turns, this will not go in the anti-ferromagnetic, but it will go because the exchange goes through this atom, through this atom to this atom. So, it is not between just these atoms, between these two you have only one atom, between these two. So, here you have changed the angle. So, therefore, there is a flexibility, and this orients in such a way that is both the vectors will be in the same direction. So, therefore, you get, so this is on. So, ferromagnetically coupled kind of thing. Now, this is another central moiety connected to this ligand, connected to this ligand, connected to this ligand. So, you can see the M. So, we can have M as copper 2 plus, M as cobalt 2 plus. Will it differ? Yes, because the geometry that cobalt tries to enforce is more of a tetrahedral, and the geometry of the copper that enforces is the square planar. So, because of that, this your orbital overlap will change. So, in case of copper, the value is very small, J is coupling very small, almost antiferromagnetic, but not 100%. So, and the J is a bit more greater, you see that the kind of a thing. So, here this orbital is more or less into this orbital is little away from that. So, this makes the difference. So, the d orbital alignment with respect to the p orbital alignments of the connected ligands will determine the orientation, and the spin orientation will determine whether it is a ferromagnetic coupling or the antiferromagnetic coupling. I hope that is very clear to you, the magnetic coupling. So, as I told you, it is depend upon what is the connecting moiety and how flexible they are, and what way these magnets can orient magnetic fields. So, the same thing is shown here, ferromagnetic here is 180-degree value, nickel ONi, I showed you for the manganese in the previous case, this one. So, it is a perfect linear. So, therefore, this vector induces this vector induces this, these two are opposite, these from the D, these from the D, these two are opposite. So, therefore, antiferromagnetic. Here it is the metal, it is the oxygen, it is the metal. So, the angle is 90. So, NiO Ni is a different compound you can think of. So, in this case, this will induce this will induce that will induce. So, this and this are in the same direction, therefore, ferromagnetic coupling. So, therefore, you can get the ferromagnetic coupling, antiferromagnetic coupling, all of these depend upon the spin orientations of all of these. Okay. I hope you got some idea about the magnetic coupling when you have two paramagnetic centers present in the same compound in that. Of course, between the molecules also, when you have a lattice, that also is a similar kind of phenomena, the distance, overlap, all these things. Now, some of the molecules you can place on something and then bend more or bend less kind of. So, that is what the situation. So, for example, if you take nickel acetate ACAC twice in a 3-dimensional 3D system, it gives a 3.15 Bohr magneton, which is reasonably in agreement with the 3.23 experimental value. Now, if you put this into a 1D kind of thing. So, how do you make this nickel acetate 1D? Put on this carbon nanotube. This is a carbon nanotube. You put this compound on that. You dip in this, so the compound will get deposited on that, and then there is some kind of a geometrical adjustment in your compound. That is what is happening. The nanotube, which has a 2.1 nanometers diameter. So, then that will give, this is one reduced to 2.68 for the 1D nickel acetate at this particular nanotube, which is a 2.1 nanometer, and this will go further down. So, from 3.15 it goes to 2.68, from 2.68 it goes to 2.27, and that means 70%. There is this is another nanotube with a 1.3 nanometer. So, you are putting some kind of a constraint, a pressure on this particular molecule to bend differently, to get stretched out differently depending upon the surface. The surface inclination will change depending upon the diameter. The one which is having a 2.1 have a greater surface, bend will be slow, and the bend will be faster if you have a diameter is less, that we know. So, and the molecule is forced to sort of assume that particular surface. So, that means surface is applying a pressure to readjust the structure. So, that is what we mean by strain engineering, engineering the strain into that. So, this is important in understanding the super exchange coupling. So, all that coupling which we have studied is called the super exchange coupling. That is all the meaning is. That could be a ferromagnetic, that could be antiferromagnetic in a distorted ligand geometry. Now, here the geometries are distorted by placing just in simple solid, that is 3D you referred at, 1D put on surface, each molecule on that, on the surface of a nanotube with a greater diameter, a nanotube with a narrower diameter. So, the narrower diameter has brought greater reduction, bigger diameter brought some reduction, but not as much great as that. So, it is very clear that it is opening up, bending. So, the strains are changing in these things. So, distorted ligand geometry, which is central for many advanced materials, superconducting cuprates and their strain engineering. Now, the molecule may have in its three-dimensional structure one kind of a magnetic interaction, but now for the same molecule, by placing on different kinds of the support, here it is used carbon nanotubes. So, you can use a planar, you can use a slightly bent, you can use a strong more bent, variety of is not only carbon, you can put on many other surfaces too, where you make the nanocomposites. So, that means you are bound to change their super magnetic exchange, therefore, their magnetic properties. That is how they become the kind of a materials. Okay. I think we need to continue this a little longer to understand this coupling, because it is very important in the materials kind of a dimension. So, I will give you how such kind of things can be manifested in making the materials in the next class. Thank you very much.